today we're going to start talking about the terrestrial planets, and we'll really focus on the Earth. So if you've taken an Earth science or a geology course, then a lot of this should be familiar to you. But we'll put it into the context of how can we compare the geology of the Earth to other planets in the solar system. So we'll start with Earth and mainly focus on Earth today, and then we'll move to the other rocky planets next time. But first, we learned about all the other things in the solar system that aren't planets, and so let's see if you remember put these in order from closest to the sun and work your way out from there. So the two belts are the closest. The asteroid belt is closest. It's made out of rocky material. Kuiper belt is beyond Neptune's orbit. It's made out of icy objects. And then the Oort cloud is kind of a spherical shell of debris that's also icy, that's even farther from the sun. Okay, so if we want to look at the geology of the rocky planets, we'll start with Mercury. So if you look at the surface of Mercury, there's lots of craters. There's also areas that are relatively smooth, and then there are these cliffs that we need to try to explain. Venus, if you just look at it through a telescope, you can't really see the surface because it has a very thick atmosphere that blocks visible wavelength light, but you can use radar, which is radio waves, to penetrate the clouds and look at the surface. And when you do that, you'll see that there are not very many craters on the surface of Venus, but there are a few volcanoes. On Mars, you can see some craters, there are volcanoes, and you can see what looks like dry riverbeds. So, evidence that there was some interesting stuff going on the surface of Mars sometime in the past. On Earth's moon, we see some craters, some smooth areas, but other than that, not very interesting geologically. And then we get to the Earth. The Earth has just about everything you can think of. It's got volcanoes, it's got craters, it's got rivers, it has mountains, it has oceans, very geologically active. So our goal is to try to understand why all of these objects should have formed around the same time at the beginning of the solar system. So why did they all have different features, and especially the Earth, why is the Earth so active when all of the other rocky planets are seemingly not as interesting? So we'll start really the rest of today focusing on the Earth as a planet, and we'll talk about why it's geologically active and what those geologic processes and how they shape the Earth, and then we'll talk about Earth's atmosphere. If you look at the cross-section of each of the planets and the moon, you'll see vaguely similar features. So there's going to be some type of metallic core at the center of all of the inner solar system objects. And then where it differs is what's outside of the core. So for Earth, Venus, and a bit of Mars, there is a mantle that is not completely hard. So it's it's still made out of rock, so it's not necessarily a liquid, but it's rock that is capable of deforming and moving because it's very hot and under a lot of pressure. If you look at Mercury and the Moon, they don't have that mantle of rock that can move, basically. So the layer of the planet that includes the rock, the solid part, the very solid part of the mantle, and the outer crust is called the lithosphere. And you can see for the geologically more active planets like Venus and Earth, the lithosphere is a very thin layer, but then as you become less geologically active, the lithosphere basically goes all the way from the surface towards the core. So in order for you to have some kind of geologic activity, there has to be this mantle layer where rocks are able to move more freely, and they're not completely solid. So Earth's core is very high density. It's made out of nickel and iron. So if you look at the periodic table, you'll see iron is part of the way down and nickel is a little bit denser than that. And when we talk about stars doing nuclear reactions, we'll learn why there's so much iron available for Earth's core. Then out from the core, there's this mantle. Again, that's going to be rocky material, but it's going to be under extreme heat, and so those rocks will be not quite a liquid, but also not quite solid either. And then the lithosphere includes the crust, where you have your solid rock material. That's what we're standing on. That's what all life exists on, basically, or in the ocean. And so the density goes highest density towards the center, and then less dense as you move out from there. This different densities of materials at different layers is called differentiation. And so this is one of the core things that an object needs in order to be a planet. So your object has to be made out of different materials, and then, or different densities of materials, and then those different densities have to stratify into most dense towards the center, and then less dense out from there. So what do you need in order for an object to differentiate? So it's two answers are correct. So you have to be made out of different materials, and then those materials have to be able to move past each other in order for the denser ones to go towards the center and the lighter ones to be closer towards the surface. And it doesn't necessarily have to be metal and rock. When we talk about some of the moons in the outer solar system, those will be made out of ice and different densities of icy material, we'll also be able to differentiate. So the lithosphere is this outer region of the Earth that includes a little bit of the mantle and then the rocky crust. And this is, you can think of it as floating on the material underneath of it. So again, the mantle is not really a liquid, it's still a solid, it's just kind of in between a solid and a liquid, if you want to think about it that way. And so all of your, we'll talk about plate tectonics later, all of the plates that the continents rest on are going to be part of the lithosphere. And the reason you have plate tectonics and your surface can move is because it's resting on this mantle. So when you think about rocks, you probably think about just a hard object that doesn't ever change its shape. But the rocks that are in the mantle of the Earth are under very high temperatures, and so those rocks are not necessarily completely solid. You can stretch them, you can pull them apart, you can break them, and because they are what we would call plastic, they can move basically. So you can, if you just had two solid rocks sitting on top of each other, they could never move past each other. But because they're kind of squishy and can be stretched, you can move different densities of these rocks in the mantle past each other, and that'll be important when we talk about how heat cycles through the center of the planet. So what causes the geologic activity on the Earth is actually heat cycles. So in the mantle, because the rocks are able to move past each other, you can have the rock that's closest to the core is going to be the hottest. Hot material is going to rise. The material closest to the crust is going to be colder. That material is going to fall, and you get these convection cycles. So convection is just this circulation of hot material flowing up and colder material flowing down. If you were to track, let's say you had one particle of the mantle up near the crust, and you were to track that particle through its whole cycle of falling down towards the core, heating back up, and then rising again, that process would take 100 million years. But this convection cycle is always happening. So there's always some particle that started closer to the core and is now closer to the crust, and they're constantly cycling hot rising and colder material falling. So you need to have some source of heat in order for your planet to remain geologically active. When you start forming your planet, you are basically compressing a bunch of material into a smaller region, and so you're converting gravitational potential energy into heat energy. So that is the energy left over from your planet forming. So that's only really going to power your internal heat of your planet in the early stages of formation. Next, your planet is made of these different densities of material, and the denser objects want to go towards the center of your planet, and the less dense objects want to be on the outer part of your planet. And so there's going to be some energy associated with the denser things moving towards the center and the lighter things floating towards the top. But again, that's only going to be able to provide you enough heat to power your planet's geologic activities right after it formed. So we think today the heat that's being generated by our planet is from the radioactive decays of elements closer towards the center of the planet. So this heat that's generated in the interior of your planet is not an infinite resource, and you lose some of that heat to space. So the convection cycles are bringing heat from the core towards the surface, and that's convection. So convection, you need a material that can cycle like this, whether that's a liquid or a gas, or in the case of the mantle, kind of something in between a liquid and a solid. Then the heat passes through the crust through conduction. So conduction, you need a solid material. Then from the surface of the planet, the energy is radiated out from the surface and into space. So in this picture, you have kind of the three main ways that heat is transferred: convection, conduction, and radiation. And radiation is the way that the energy of the planet is slowly being lost over time. So even if you had energy from your gravitational collapse forming your planet and the differentiation of the denser materials sinking towards the center and the lighter materials going towards the top, eventually that heat is going to be dissipated into space. And so if you don't have some other source of energy, your planet will cool off and no longer be geologically active. So conceptually, which of these objects will cool faster? Yeah, so the smaller amount of heat basically that you start with will mean that you cool off much faster. Let's apply that analogy now to planets. So is this true or false? So a small planet cools faster than a large planet. Yeah, so the smaller cup of coffee cooled faster, the smaller planet is also going to cool faster. So when we look at the terrestrial planets again, you'll notice that Earth and Venus are the two largest, and they are the two that are the most geologically active. So the Moon is the smallest. It is not geologically active. Mercury, the next biggest, also not geologically active. And Mars is kind of on the cusp of it is either very recently geologically active and is now dead, or is like very minimally currently geologically active. There's debate about whether Venus is currently geologically active or not. It's very hard to study Venus because it has a very thick atmosphere and we can't send probes there. But we think it either was very recently geologically active or is still active. And then Earth, of course, is still very geologically active. So you need, not only do you need all of your different materials with different densities, but you need whatever mass your planet started with to be fairly high in order to maintain geologic activity. So this comes down to a physics idea called the surface area to volume ratio. And so this equation, the top line, the surface area of a sphere is 4 pi r squared. The volume of a sphere is 4/3 pi r cubed. So if you divide those two things, you're left with a factor of r in the denominator. So because the r is in the denominator, if you increase the r, or the radius of your planet, then you're going to slow the cooling down, basically. So smaller objects will lose their heat faster, and the bigger objects will have a smaller ratio, and so they cool more slowly. And so the reason we care about surface area to volume, the surface area is the surface that you can radiate your energy out into space, and the volume is where the heat is coming from in the center of your object. And in order to be a planet, you have to be a sphere, so the surface area to volume are going to be for a sphere, and we don't have to worry about other shapes. So in addition to geologic activity, we can look at magnetic fields around planets. So you might have seen a magnet in an introductory science class. You've got a north pole and a south pole, and if you drop a bunch of iron filings around your magnet, you can trace out the magnetic field lines that go around the magnet. So this is a permanent magnet. You can also make a magnet by wrapping a coil of wire around a piece of metal and then running a current through that wire, and you get the same type of magnetic field. So that's an electromagnet. And the Earth is not quite an electromagnet, but it also generates a magnetic field by having charged particles rotating about a metallic core, basically. So instead of wires generating a current to go around the piece of metal, you just have charged particles that are spinning around the center of the core of the metallic core of the Earth. And the only way that you can get a magnetic field is if the inner parts of your planet are still able to move with respect to each other. So you need geologic activity, basically, in order to maintain your magnetic field. And so there's the most striking evidence for Earth's magnetic field are the auroras. And so an aurora occurs when you have particles coming off of the sun that are charged. They will interact with the Earth's magnetic field lines and spiral in towards the either north or south pole. And as a charged particle spirals, it is accelerating, and an accelerated charged particle will emit radiation in the form of light. So the northern or southern lights are a consequence of charged particles from the sun interacting with Earth's magnetic field. And if you ever get a chance to see the northern lights, I would highly recommend it. I have never seen them in person, but I mean, this just looks really cool. So obviously the further north you go, the more spectacular they're going to be. But it's also not really a trip you can plan, like I'm gonna go during Northern Lights season. There isn't really a season, you just kind of have to get lucky that there's enough activity coming off of the sun to create the aurora. But definitely on my bucket list for things that I would like to see. I've told you what the inside of the Earth looks like, but how do I know that? How do scientists determine what the interior structure of a planet is? So one of the ways that you can study the inside of a planet are by studying earthquakes. So when we talked about electromagnetic waves, we said that your electric and magnetic fields oscillate, and then the velocity or the photon travels perpendicular to those oscillations. So that would be an example of an S wave. But there's a different way that waves can propagate that are called P waves or compression waves. And in that type of wave, the direction of motion and the direction of oscillation are the same direction. So if you take a slinky and vibrate it back and forth, then you have a P wave, but if you take a slinky and oscillate it up and down, you get an S wave. So these different waves will actually travel differently through whether you're talking about a solid or a liquid. Let's say the earthquake is happening on the left side of the planet. It's going to generate P waves and S waves. If you track the different waves coming through the planet, not all of the S waves will make it from one side of the planet to the other. So some of the S waves are traveling through the mantle. All of the P waves make it through whether they go through the mantle or the core, but some of the S waves that are trying to get through the core don't make it. So remember, the mantle is this kind of in between a liquid and a solid, and S waves can only travel through a more solid material. P waves can make it through solid or liquid. So the fact that the S waves stop instead of traveling through the center of the planet tells you that there's some liquid material in somewhere that's blocking the path. And so we think that there's a solid inner core, there's a liquid outer core, and then there's the mantle, which is rock, that is highly viscous, so it's really hard for it to move, but it still is able to move a little bit in order to do those convection cycles. So that's how we know what's going on inside of the planet, but maybe you're more interested in where you live, which is on the surface of the planet. So what kind of processes make the surface of the Earth different from the surfaces of the other terrestrial planets? So the geological processes that will shape the surface of a planet, there are a few different ones. Impact cratering, so this is objects from outside of your planet, from space, hitting the surface. Volcanism, so you can have some of that material from the mantle erupting up through the surface. Plate tectonics, so you can have the parts of the crust move with respect to each other, and that causes a lot of features on the surface. And then erosion, if you have wind, water, or ice, you can break down material and move it from one place on the surface to another. So we'll see examples of all of these. For impact cratering, most of this activity happened very early on in the solar system. So when there were a lot of objects that were not yet merged into a planet or safely away in the asteroid belt or Kuiper belt, there was a lot of material around all crashing into each other. Now there's a lot less impact events happening in the solar system. When an object hits the surface of a planet, it makes a crater that's about 10 times wider than the object itself. And when you look at the surface of planets, you'll see that there are a lot more small craters than there are large craters. And that's because there's a lot more small impacting bodies than there are larger impacting bodies. So here's a couple of examples. This is Meteor Crater in Arizona. And this is Tycho Crater on the moon. So there are lots of different types of volcanoes. We won't get into all of those today, but in order for a volcano to exist, you need to have some kind of molten rock underneath of the surface, and then through some process, the crust will be thin enough that that molten rock can travel to the surface. And when that molten rock does make it to the surface, we call it lava after that. And that lava can erupt and flow on the surface and create new features. But it's not just the molten rock that can come up from a volcano. You can actually get a lot of gases being released from volcanoes as well. So when we talk about the conditions that you need for life to exist on a planet, this is going to be a very important thing to remember. For plate tectonics, so you have the convection cycles happening down in the mantle, and the crust is sitting on top of that mantle and kind of floating on top of it. So if you look at these two convection cycles, they're kind of pointing towards each other, and so you're going to get material pushing together, and that can form mountains. And then if you look at the two convection cycles on the right, they're pulling apart from each other, and so the crust in that area is actually pulling apart and making it thinner. So the compression of the plates can create mountains like the Himalayas, and you can get rift valleys like in East Africa, where the plates are pulling apart from each other, and you can get valleys or new continents or new seas forming in those rifts. And then erosion is just a blanket term for processes that will break down rock and move it from one place to another. And there's a few different ways that you can do that. Glaciers can do it, rivers can do it, and the wind can do it. So if you've ever been to the Grand Canyon, the Colorado River has been carving the canyon for millions of years, and that's an example of erosion by water. So if the river started at the top of the canyon walls millions of years ago, over time it's cut through the rock and has transported it somewhere else, and now you have a big canyon left over. Glaciers can also carve out landscapes. So this is Yosemite Valley, and so when during one of the ice ages, there were huge glaciers extending pretty far south on the surface, or pretty close to the equator on the surface of the Earth, and so those glaciers carved out the softer rock and left behind the rock that was harder than the ice was. And then wind erosion will break down larger rocks into smaller particles like sand, and you can build up sand dunes or weather away the peaks of mountains. But erosion is not necessarily only a destructive force. You can also, that the stuff that eroded has to end up somewhere. And so in the case of a river, the material is going to be deposited at the end of the river in a river delta. And so this is new land being made basically from all of that eroded material. And some of the most fertile cropland on the earth is in river deltas, so very important for human civilization. Okay, so the last thing that we'll talk about is Earth's atmosphere. So we've talked about the geological processes, so the stuff inside of the Earth and the stuff on the surface of the Earth, and now we'll talk about the atmosphere that's around the Earth. So amongst yourselves for a couple minutes, you can think about how the Earth's atmosphere affects the Earth. So somebody said protection, so it's a very important source of protection from radiation coming from space, especially from the sun. So all of the X-ray radiation from the sun is absorbed very high in Earth's atmosphere. Ultraviolet light penetrates farther into the atmosphere, but it is absorbed by a layer of ozone kind of in the middle of the atmosphere, and then visible light makes it all the way through the atmosphere to the surface. So if anyone remembers, back in the 90s, there was a hole in the ozone layer caused by chemicals, especially associated with like hairsprays, and if you have a hole in the ozone layer, then ultraviolet light is going to hit the surface, and any high energy photons that interact with living cells have a chance to cause mutations, and that's very bad for life. So this is how you can get skin cancers, and even worse than that, if you have enough high energy radiation, then you just would kill any life that exists before it really had a chance to do anything. So the atmosphere is very important for protection from high energy radiation. However, that makes doing astronomy kind of difficult from the surface of the Earth. So if you want to look at gamma rays, X-rays, or ultraviolet light coming from space, you're not going to have a good time trying to do that from the surface of the Earth. If you want to study space in visible wavelength light, you have a good shot. And even in the infrared, there's some windows that you can look through that you can see light from space. And then radio waves also penetrate through the atmosphere. But if you want to study those higher energy photons, you're going to need to launch some kind of satellite into space in order to study them. So Fermi, Swift, and Chandra are all high energy space-based telescopes that we've launched. But you can also launch visible wavelength telescopes like the Hubble, just so you don't have to deal with atmospheric effects impeding your observations. So when we talk about telescopes in a few weeks. We'll talk about the designs of these different kinds of space telescopes and why you would even want to launch something into space. The other important effect that the atmosphere has is the greenhouse effect. We'd said that the visible wavelength light can pass through the atmosphere and make it to the surface. Some of that visible light is going to just bounce off the surface and either go into space, or maybe it hits a cloud or something. But some of that energy is going to be absorbed, and there's also heat energy coming from the center of the planet that's being conducted through the crust and is leaving the surface. And the energy that's being radiated from the surface is not a visible wavelength light, it is an infrared wavelength light. It turns out a lot of particles in the atmosphere are actually very good at absorbing infrared light and not letting it escape back into space. So we call those greenhouse gases. Water is actually a greenhouse gas. Carbon dioxide is, methane is. So basically the molecules that are two different chemicals together are greenhouse gases, but the pure things like oxygen and nitrogen are not greenhouse gases. The problem with greenhouse gases is if I'm trapping the infrared heat from the surface of the planet that should be radiating back into space, I'm slowly going to heat up the surface of my planet. And so Venus actually had a runaway greenhouse effect in its atmosphere, and so that's why Venus is the hottest planet in the solar system, even though it's not the closest. Mercury is closer, but Venus is hotter because it had a runaway greenhouse effect. And if humans are not careful, we could suffer the same fate, and that would be not good. Okay, so another consequence of Earth's atmosphere is why we see a blue sky during the day. So we said that the visible wavelength light will pass through the atmosphere, but there are different wavelengths of light that make up the visible spectrum. It turns out the particles in the atmosphere are really good at scattering blue photons. And so if you're looking kind of during the middle of the day, when you look up at the sky, you see it as blue because there are blue photons that have scattered basically in all directions. And so when you look up, there's a blue photon coming from basically any direction you can imagine, hitting your eyeball, and that's making the sky appear blue. When you're closer to sunset or sunrise, now the red light is going to be coming straight into your eye because it's not getting scattered, and the blue photons are still getting scattered, but it's no longer blue light coming from every direction. Some of the scattered light is not hitting your eye at all. And so you get these red sunsets, but you have blue skies during the daytime. So the sky is blue because the particles in Earth's atmosphere scatter blue photons more than they scatter red photons. It's not because the particles themselves are blue or because the atmosphere is reflecting Earth's ocean. Nothing to do with that, just scattering of light in the atmosphere. So the atmosphere is responsible for some of the erosion on the Earth due to rain or wind. It protects you from harmful radiation from space. the greenhouse effect can keep the surface warm, but you can also have a runaway greenhouse effect that makes the surface too warm, and it also gives you nice blue skies. Other planets have different atmospheric compositions and they don't have the same blue skies. So why is Earth geologically active? Because it was big enough to retain a lot of its heat, or the mantle is still molten, and the geologic activity is keeping things moving, so that's keeping the plate tectonics going, and that will be important later on when we talk about life on a planet. And the fact that things are still moving means that you can get charged particles moving around the solid metallic core, creating a magnetic field. And you can have impact cratering, volcanism, plate tectonics, and erosion changing the surface of the planet. And then Earth's atmosphere also does erosion, protects you from radiation, and can heat things up through the greenhouse effect. So now that we know more about the Earth, we're going to use that to compare and contrast with the other terrestrial planets in the solar system.